Hello everyone, I welcome you all on Data Phoenix webinar. Sorry that you're waiting for us. There was some sharing problems and we try to fix them and for now find solution and we can start. I'm welcome today Harpreet Sahota. He is developer relation manager at DESI. And today we will talk about fine-tuning and configured base language models. You can ask questions using Slander, and don't forget to subscribe to our channel to see all videos and participate in all our webinars. So I give the microphone to our speaker and we will start.
Hi, what's up, everybody? Super sorry that it took forever to get started here. Just some issues with sharing, and it took me far too long to think of this solution, but it worked. Long story short, couldn't share my screen through Restream. I had my presentation done in Keynote, but then I had to convert it to PowerPoint and get it up on Google Slides. But we're here. We're here now. Let's get started. Let's get right to it. I'm not wasting no more time. Just a little something about DESI at a glance. If you haven't heard of us, you can Google us, look us up. I'm going to skip through these slides in a hurry, but we build models. That's the thing that we do. We got this inference kit called Inferri that's proprietary, so it's not open source. So that's about that. We've got a bunch of models on HuggingFace. Check us out on HuggingFace. Like the models, check them out. We got a bunch of models actually dropping next week. A few language models and another diffusion model. So keep an eye out for those. Here's just some information about the model that we're going to be working with today. This is a DESI LM 6 beats or 6 billion parameter language model. The first language model to use group query attention, even though Mistral gets a lot of hype for it. We use group query attention before Mistral did. So just a little bit about Inferri. That's it. We're going to skip over this. Here, let's just talk about what we're going to talk about today. Let's get right to it. This is the agenda for today. The agenda is what it is because I'm making zero assumptions about your background knowledge. My only assumption is that you know what a LLM is. Some of you might already be familiar with these topics. If so, great. This is going to be a recap for you. Use this opportunity to leave smart or insightful comments in the chat while I go over the slides. But if you're unfamiliar with any of the stuff on this slide, that's also great because you're going to learn about them during the talk. Heads up, there's a fair amount of talk, like 20 slides of talking before we get to code. This is absolutely necessary, right? We need background context and mental models of what we're doing before jumping into the code, always. So I'm not going to go into super mathematical depth or detail. We have less than an hour together. How can I possibly do that? I can't. But what you're going to have is a richer vocabulary of search terms so you know what to look for if you want to go and look for more depth. And you'll also have a mental model of what fine-tuning process comprises. So hope you're ready. Let's go. First things first, the difference between a base model and instruction 2 model, right? So, but even before that, what the heck is pre-training? What is fine-tuning? So pre-training just involves exposing a model architecture to obscenely large volumes of text data, books, articles, web pages, et cetera, et cetera. And during this process, the model is learning to predict the next word in a sequence, and it's also learning connections and patterns between words, concepts, and ideas from language. The more tokens the model sees during training, the better it's going to become at generating new content. Essentially, it's like teaching the model basic rules and nuances of a language and kind of giving it an internal world model of the human language. But after the pre-training process, you're left with this artifact, and that artifact is a base model. And this base model is what you can then take and fine-tune for further downstream tasks. So fine-tuning essentially is just continued training of a pre-trained model on a specific, usually smaller data set. And this is a step that allows a model to adapt to specific contexts or needs of a particular application or task. And so during this process, the model's parameters are going to be updated based on what it's seeing in the new data set. And you're going to focus on specific input-output pairs that's going to help guide the model towards some desired behavior. So it really is this fine-tuning step that's going to mold the model's behavior for specific tasks while retaining its general knowledge. In general, language models come in 3 different varieties. There's the base model, instruction-tuned model, chat-tuned model. In general, these are the 3 different types of large language models you'll see. Base LLMs, like the one we're going to see today, DESI-LM6B, are just models that are trained on large and diverse data sets. They're great at understanding and predicting language patterns, but they don't always follow specific instructions or prompts. So, for instance, they can generate high quality content on a topic. They might not follow instructions like, talk in this tone or, only use these keywords. But an instruction tuned LLM, this is going to be able to kind of follow more instructions. It's going to undergo additional training on more narrower data sets. And this is going to improve the model's performance, especially for following instructions. Chat tune model, if you played around with Chat GPT, then you know what it's like to interact with the chat tune model. I don't need to go into too much detail there, but there's a subtle difference between a chat tune model and an instruction tune model. Specifically, the chat tune model is geared more towards natural language kind of conversations, right? So it's just more kind of natural, coherent, engaging responses in a conversational manner. Let's just make this distinction clear with a couple of examples. So what I'm showing you here, this is the generation from a base model, in this case, DESI-LM6B. You can see that the generation just goes on to complete the text in the prompt, but it's not following the instructions, right? Here I'm saying how to make a good trap beat, right? Like it's kind of an instruction, kind of a question type of thing. And the base model is just predicting kind of the next token it thinks should occur in this sequence based on what it's seen in internet data. The next output here, this is the output actually from a instruction tuned model. In this case, the official DESI-LM6B instruct tuned model. And as you can see here, it's actually following the instructions and telling us how to make a trap beat. And that's what we're going to learn to do in this session. We're not going to learn to make a trap beat. We're going to learn to start with a base model and then instruction tune it. But before we do that, it's also more important to just clarify some key terms. So I just want to define some jargon. We know the difference between pre-training fine-tuning, base models, and instruction-tuned models. There's a few more terms that that you will hear thrown around if you're hanging around large language models long enough. And those are these terms here: prompt engineering, full fine-tuning, retrieval augmented generation, and parameter efficient fine-tuning. So prompt engineering, it's a method that focuses on crafting and refining the input given to the model, and we're carefully designing prompts. And in this way, we're guiding the LLM to produce outputs that are more aligned with our desired results. So prompt engineering, we're not updating the model's weights or updating the model's parameters in any way, right? We're kind of just trying to steer the model towards some desired behavior, just using the context window. So this is also something known as in-context learning. You might hear it called that. Then there's retrieval augmented generation, and this is just essentially combining the principles of prompt engineering with like the principles of information retrieval and querying of databases to provide additional context to a model. So it's enhancing the LLM's ability to provide answers that are not only contextually relevant, but also just rich in detail, rich in accuracy. Full fine-tuning is just updating all the parameters of a LLM using a specific data set for the task at hand. It's a very comprehensive approach, and it's customizing the entire model for specific requirements. And then there's parameter efficient fine-tuning. And this is just kind of modifying a subset of the model's parameters, and it's making it more, it's just a more efficient approach for adaptation. And it's leveraging the existing broad knowledge of the language model while fine-tuning it for specific tasks or applications. So just a side note, pretty soon, if you're on LinkedIn Learning, you'll see a course from me on prompt engineering. I did a course called prompt engineering with LangChain. That'll be out soon. I'm doing another course for them called retrieval augmented generation with Llama Index, and I'm also writing a book about retrieval augmented generation with Wiley Publication. So keep an eye out for those things. I'm going to breeze through these next few slides because I want to get to the good stuff, and I've wasted already too much of your time. But this is what this is what prompt engineering does. We're just shaping the model's output without training the weights, without updating the weights or anything. And this oftentimes gets us good enough accuracy for many applications, but it's kind of limited in robustness. Downside is that it's not, you know, completely accurate or robust enough for use cases that need additional background knowledge. And that's where retrieval augmented generation comes in. And this is retrieval augmented generation. Essentially, it's coupling information retrieval with text generation methods. So we have we need a vector database, right? So we have some internal data set that we have. When you take this internal data set, we need to chunk it up, split it up, embed it, put all those embeddings into a vector database. Then user query will come along. We're going to take the user's query, which is in the form of a prompt. We'll take that query, we'll embed it, then we'll search for relevant documents in our vector database. Then we'll bring those documents into the context window, and then kind of have the language model reason over this additional context and give us an answer. So that's what it is at a high level. Full fine tuning. Let's spend a little bit more just time talking about this, right? So let's just assume that we have a language model, and now we want to take this language model and we want to get this language model to be like really good at understanding biotechnology. So we might start by collecting a set of research papers from the target domain of biotechnology. So we're going to then fine tune this model to be able to take like a full on research paper, full on body of text, and fine tune it so that it's able to create an abstract, right? So we're going to need a couple of different inputs, so to speak. We'll need a full paper with its original abstract, right? Then we're going to need to take this paper. We're going to need to just, do some processing of it, ensure that it's in a format that's going to be good for the model. And then we're going to then pick a base model. We're going to load in that base model, decide on some hyperparameters for fine tuning, like, learning rate, batch size, number of epochs, so on and so forth. Then we train the model. So we're going to feed this pre-processed content to the language model as input and train it to generate the corresponding abstract as output. Then we can, monitor the model's performance on some validation set, and make sure we're not overfitting or anything like that. Then once fine tuning is complete, we're going to assess the model's performance on the test set. And you might use some metrics like Blue or Rouge, or whatever human evaluations to measure the quality or relevance of these abstracts. And then you just kind of iterate until performance is satisfactory. This is great, but it's not without its um, an entire set of limitations. There's some issues with it. So full fine tuning is updating all parameters of a large language model. So this is going to require an immense amount of compute because we have billions of parameters. And even on small data sets, this becomes really, really costly to do, time intensive, costly. GPU. When you're spending time on GPUs, time is money, right? So ends up being costly. You also need a lot of memory requirements because you need high-end GPUs or high-end TPUs with huge memory capacities. And this is often pretty impractical for a lot of businesses because of those hardware demands. Not only that, you probably require some specialized expertise because, if you're working with these large language models and you're doing full fine tuning, you're going to have to worry about having somebody that's good at doing like distributed computation and distributed training and all that. There's also the issue of catastrophic forgetting. You might, you know, models can kind of forget previously trained knowledge if they're trained on a new or different data set for long enough. And this becomes a problem when the model is required to remember kind of information from multiple different tasks. And this is going to lead to, loss of information from previous tasks. The fine-tune model, is going to contain as many parameters as the additional model. And so this becomes burdensome because you need to store all those model's parameters each time you train the model or retrain the model on a new task. So again, it becomes very memory inefficient and really intensive. Not to mention like the issues with hyperparameter tuning and experimentation and all that. And this is where given the limitations that we just discussed, we need a better way. And by better way, I mean um, you know something that's more compute and data efficient. And we need a method like this so that we can fine tune our model. And so there's been a lot of research done in this area. And the core idea that's emerged is that you can actually fine tune a model by adapting only a small portion of the model parameters or adding in some new parameters, some adapter layers during fine tuning. And this is what we call PEFT, parameter efficient fine tuning. So PEFT is actually a set of techniques that you can think of as like focused fine tuning. So during fine tuning, PEFT is going to selectively update only a few of the model parameters. And this is based on the understanding that, a large pre-trained model already has a pretty good grasp of language constructs and knowledge. So we don't need to adjust the entire model for a specific task. So PEFT is, a more resource efficient way of fine tuning because you can concentrate on fewer parameters rather than fully tuning all of the model parameters. And then some methods of PEF just focus on adjusting either some original small portion of the original parameters, and others just add in and train new components like adapter layers, which are going to enhance the model's capabilities without altering its core structure. And in this session, the specific PEFT method we're going to focus on is called QLoRa. So QLoRa was introduced in May 2023 in a paper by Tim Detmers and others, and it was called QLoRa, Efficient Fine-Tuning of Quantized LLMs. So QLoRa stands for Quantized Low-Rank Adaptation. So it's a PEFT method that just really reduces memory usage and allows for fine-tuning of large language models to be more accessible and more efficient, because QLoRa essentially is slashing resource requirements. So by slashing resource requirements in the form of memory and compute needed, that means that more people can experiment and develop with these large language models. So this means that researchers and practitioners who are GPU poor, like me, who have limited resources, can participate in the field and participate and kind of help push it forward and just play around with these models. And in fact, in the paper, they took a 65 billion parameter model and they were able to take this model and train it on a single 48 gigabyte GPU while preserving performance. And so in a bit, we'll talk about why that's impressive. But how does it work? It under the hood, it uses something called low rank adaptation. And so low rank adaptation is going to modify a small set of model parameters while leaving most of the parameters kind of untouched or frozen. So this is operating under the hypothesis that weight changes during model adaptation are inherently of low rank. So this means that only a subset of features need updating during fine-tuning. So that probably begs the question for you, like, what does rank even mean? So let's talk about what rank means. So essentially, the rank of a matrix is going to tell us the dimensions of the space spanned by its columns or its rows. And this is determined by the number of linearly independent columns or rows in a matrix. So if you recall from linear algebra, linearly independent means that no column or no row in a matrix can be created by taking a linear combination of another column or another row. And by linear combination, I mean like multiply by some number and add it, or something to that effect, like linear transformation. So linear combination rather. And so when a matrix is full rank, that means its rank is equal to the smaller number of its rows or columns. And so this means that all the rows or all the columns are linearly independent of each other. So a low rank matrix has a rank that's less than the smaller of its rows or column counts. And this indicates that some of the rows or columns can be expressed as a linear combination of others. And so we call this a rank deficient matrix. So when we fine tune a large language model, we're modifying the underlying parameters of the model. So let's assume that we have a 7 billion parameter large language model that is represented by this weight matrix W here, right? During training, during backpropagation, we're actually learning this weight update matrix, delta W. And so delta W just contains information on how much we want to update the original weights so that we're minimizing some loss function during training. So essentially, you could think of this at the end where you're going to add this weight matrix, this delta W weight matrix to the pre-trained weights, and this is going to give us some updated weight matrix. All right, so like I said, like our original weight matrix, suppose it contains 7 billion parameters. So that means that our update matrix, delta W, also has 7 billion parameters. All right, so you can see how this is adding up, and this is going to make the computation of this matrix, very compute and memory intensive. And this is where LoRa comes in. And LoRa was proposed in 2021 in a paper called Low Rank Adaptation of Large Language Models. And this was done by Edward Hu and others. And essentially, this paper is proposing that we can decompose the weight changes into a lower rank representation. So let's talk a little bit about that. So the core idea behind LoRa is to model this fine-tuning update that we saw in the previous slide with a low rank decomposition. So LoRa is going to leave the pre-trained layers fixed and frozen, and we're going to inject a trainable rank decomposition matrix into each layer of the model. Okay, so you can think of a low rank matrix as just having fewer degrees of freedom and thus storing less information than a full rank matrix. So in the case of LoRa, the low rank matrix is going to have far fewer parameters because now we only need to store a n by r matrix and a r by n matrix. And this contains a total of 2 times r times n parameters, which is far less than n squared parameters. So that means instead of explicitly calculating that entire weight matrix that we saw in the previous slide, LoRa is going to learn to decompose the matrix directly during training. And this is going to result in a lot of savings with memory and compute. So essentially, we're breaking this down into 2 smaller matrices here. And we're going to suppose that this matrix A has the same number of rows as the pre-trained weights, right? And we're going to suppose that this matrix B has the same number of columns as this pre-trained weight matrix. And so now this delta W matrix that we saw in the previous slide, we can write that as the matrix multiplication of this matrix A and this matrix B. And so decomposing the updates as the product of these 2 smaller matrices is going to ensure that the update is low rank, and this is going to just reduce the number of parameters that we have to train. It's going to reduce it from n squared to 2 times r times n, right? And so this just essentially this decomposed matrix is just going to approximate that matrix that we would get from full fine tuning. So we start by initializing this matrix A with some small random values, and we initialize this matrix B as just completely just zeros. And then this way, we're ensuring that we begin the fine tuning process with the model's original pre-trained weights. So in the context of LoRa, low rank adaptation involves representing the weight updates during fine tuning as low rank matrices. And so this is, again, I'm just going back 1 slide. This weight matrix right here, we're going to represent it as 2 smaller matrices, right? These 2 smaller matrices are actually approximating this entire matrix here, but we're doing so in such a way that, we're going from n squared, which would be n by n, to 2 times r by n. All right. I'm just going to look and see if there's any questions in here. I don't see any questions coming into the chat, so I'll continue going on. Great. So why does why does LoRa actually work? So I did some research, and the only satisfying answer I can find was this, that despite their size, large language models actually intrinsically have low dimensions. So this means that the weight matrices of these models, they're already low rank. So not all of the parameters are actually necessary. So techniques like low rank approximation, which approximate the fine tuning update with that low rank decomposition, is going to be more lead to more efficient and effective fine tuning. So we end up with a model that has this really impressive performance despite having relatively fewer trainable parameters. So there's a lot of great stuff about LoRa, which make it awesome. We can have one pre-trained model that's shared by multiple smaller LoRa modules that are fine-tuned for different tasks. And then we can take these LoRa modules and kind of bake them in to the pre-trained model weights. So by doing that, we're not really, we're not adding to like the inference latency of the model. Fine-tuning also is just, with LoRa, is just faster and requires less memory than end-to-end fine-tuning. So LoRa also is just helping reduce the barriers of entry for fine-tuning. So again, it's just making it more accessible to take a large language model and work with it on consumer grade hardware or on hardware that you can get with Google Colab. So if LoRa is so awesome, then why do we need QLoRa? Well, the one thing about LoRa is that this was a tweet from Sebastian Raschke just yesterday, that LoRa is just becoming its own research field. There's so much happening in LoRa nowadays. So we started with the idea from 2021, and you can see over the last few years, a couple of years, that there's just been a lot of groundbreaking work that's happened. But specifically for our purposes, LLMs are just massive, right? They're huge. As a rule of thumb, you could think of each parameter in a model takes about 2 bits of memory. So that means you could multiply the number of parameters in a large language model by 2, and that'll give you roughly the size of the model in gigabytes. And that's not including the weight gradient. The weight gradient is an additional 2 bytes per parameter. Then the optimizer state is 8 bytes per parameter. So you have 2 plus 2 plus 8, that's 12 bytes per parameter for full fine tuning. So if you were to take a 7 billion parameter model and try to do full fine tuning on it, you would need 84 gigabytes of GPU RAM in order to do that. That's just a lot of memory on GPU. You need some high end hardware for that. So the reason for developing QLoRa, despite the effectiveness of LoRa, is to achieve these additional computational efficiencies and memory reduction through quantization. And that's really the core trick in QLoRa is quantization. And this is what makes it more practical to fine-tune large language models in environments with limited resources. But what is quantization? So let's talk about that. This image comes from the DESI blog, The Ultimate Guide to Deep Learning Model Quantization. You can Google that, check it out. But we talked about how LoRa just significantly reduces the number of trainable parameters in a model, but we also discussed why it still requires a considerable amount of computational resources for training and inference. And so QLoRa now has taken LoRa to the next step by introducing quantization. So quantization essentially is just reducing the precision of the numerical values in a model, which is going to lead to further reductions in computational requirements. So essentially, there are different representations of floating point numbers. Common ones used in deep learning are 32-bit and 16-bit floats. But quantization is just a model size reduction technique that's going to convert the model weights from these high precision floating point representations to low precision floating point or integer representations like 16 or 8-bit. In the case of QLoRa, though, it's going to be 4-bit precision, and is done with a new data type that's called 4-bit normal float. So by converting the weights of a model from high precision floating point representation to this lower representation, the model size, that's the model footprint, will reduce without sacrificing a ton of accuracy. So let's talk about how QLoRa works then. So it's combining the frozen 4-bit base model with some adapters on top. And we're going to back propagate through the 4-bit weights into the adapters. And to accomplish this, though, the authors invented some neat tricks for memory efficiency. 4-bit normal float, paged optimizers, and double quantization being one of those. So let's talk about those. Starting with 4-bit normal float. So 4-bit normal float was a data type that Tim Detmers had invented that will help maintain 16-bit performance levels. So this is really effective where weights are normally distributed, which is common characteristic for neural networks, because we can maintain the performance of 16-bit floating point representations while only using a quarter of the bits. So there's the awesome YouTube session. If you type in Tim Detmer's LoRA quantization into YouTube, you'll see like one of the top results is for the ML Ops learners community, and then he goes into great depth about quantization and LoRA in that session. So I highly recommend checking it out. But essentially, so the efficiency of this new data type is achieved by using a floating point like format that is using like a shared exponent across blocks of parameters and a 4-bit mantissa for each parameter. And so the shared exponent allows for something called a dynamic range that's similar to high bit width formats. So it's just balancing assignment of bit patterns to mantissa values, and this ensures that quantization is minimized. Quantization error is minimized across the distribution of weight values. So there's another technique that they invented called double quantization, which Tim Detmers in a tweet referred to as a silly technique that seemed to work. So let's talk about double quantization. So this trick, double quantization, makes 16-bit to 4-bit quantization more efficient. So it involves adding a second quantization that quantizes the quantization constants. So by applying quantization twice, first the network parameters and then to the quantization levels themselves, we're significantly reducing the bit requirements for the quantization constants. So it might seem counterintuitive to quantize already quantized values, but this process is leveraging some of the redundancy that happens in quantization levels to further compress the model without a huge loss in performance. So this technique is able to reduce the storage and bandwidth needs of quantization indices from an overhead of half a bit per parameter to just an eighth of a bit per parameter. So when you apply this to 16 and 4-bit quantization scenarios, double quantization gives a lot more improvements in storage efficiency while maintaining that computational performance that we need. So I know we're running really behind and short on time, so I'm going to breeze through the rest of these. Next is just paged optimizers. This is just a memory saving techniques. So if you have enough memory, then everything's going to stay on the GPU. But if you hit like a mini batch that's huge, that's taking up a lot of memory, then the optimizer is going to be moved to the CPU and then brought back to the GPU later. So QLoRA is awesome because we can fine tune large language models on a single GPU. That's going to cut costs significantly. We don't need high-end hardware. This makes LLM training more accessible. We're saving on electricity and other expenses with less demanding hardware. Faster fine-tuning means quicker project completion and lower costs. And we're getting these advanced capabilities without a huge financial investment. So we're going to jump into some code in a second. But here's what we need to get started with fine-tuning. We're going to need a language model, a tokenizer, a data set, 2 configuration files. We'll also need a couple of helper functions from PEFT library. That's prepare model for k-bit training and the get PEFT model functions. And then we're going to use the SFT trainers, pass all this stuff into the SFT trainers. So let us code. All right. I'm hoping you can see this A-OK. Looks like it's good there. All right, great. So we talked about what it is that we need to get started with QLoRA, language model, tokenizer, dataset, configuration files. Here I'm just getting a couple of things out of the way. These are just kind of preliminaries. We don't need to worry too much about this. Essentially, we're going to set UTF encoding so that PEFT doesn't yell at me during installation, as it sometimes will. We're just logging into HuggingFace Hub. This is not necessary, but if you want to push your model to the hub and share it, you can do so. This is just creating a directory where we're going to store our checkpoints as we're updating. So that's all that's being done here. We're just installing the things that we need. We need the PEFT library so that we can utilize parameter efficient fine tuning, accelerate to make things go burr on GPU, datasets so we can have our datasets, TRL, Transformers Reinforcement Learning Library. This is where the SFT trainer lives, transformers for our models, bits and bytes for quantization, safe tensors, and flash attention to make things go faster. So we import everything that we need. And this right here, this is the secret sauce right here. This can, like, what we put in this bits and byte configuration file is literally the only thing that differentiates different types of PEFT. So here we talk. If you remember, we talked about the few things that QLoRa introduced, right? 4-bit normal float, page optimizers, double quantization, right? And so we're setting these in the configuration file here. So load in 4-bit equals true. This just enables 4-bit quantization. So we're replacing the linear layers with, in this case, NF4 layers from bits and bytes. Here, we're using the normal float, 4-bit normal float data type. So this is just setting the quantization data type for those layers that we're going to train. Double quantization being enabled here. So this is just, nested quantization. Here, we're using bfloat 16, the brain float 16 from Google Brain. And this is just useful in deep learning because it gives us a good balance between precision and performance so that the neural networks can run faster while still producing accurate results. Here, we're just going to load the model. In this case, we're using DeciLM 6B. But when you give this a shot, next week, hopefully you will try DeciLM 7B. But we're just essentially loading the model with the quantization configuration that we defined above. We're going to set flash attention to be true. So flash attention is just focuses on the part of the model that's called the attention. And this just helps the model, attention, essentially helps the model focus on the most important parts of the sequences. So it's just making flash attention to just makes the attention computation faster and use less memory so that we can learn from more data or run on devices with less computing power. So just very useful thing to do. Here we have a tokenizer. It's going to be, a tokenizer that's associated with this model. Remember how models work. We take a string of text, break that text down into tokens, and tokens are essentially words or subwords. Those tokens get mapped to integers. Those integers then get mapped to embeddings of fixed length. And those embeddings are what get sent into the transformer model. And they get sent in parallel, right? And then the computation happens kind of on each piece of the sequence. Great. Now we're going to look at data. So one of the important findings that Tim Detmers made was that data quality is better than data quality. Sorry, data quality is better than data quantity. They found that using a 9,000 sample data set of just really high quality instructions beat using a 1 million sample data set of just mediocre quality data. This in particular, the data set we're using here, this was a highly curated data set that I put together. I initially had created it for the NeuroIPS challenge, but ultimately ended up not entering the NeuroIPS challenge. But it's essentially a mashup of 12 very high quality instruction data sets that I found on HuggingFace. And each of the sub data sets are all permissively licensed. So that's nice. None of the stuff here was generated by ChatGPT. So a lot of it was generated by Llama 2. So that makes it permissively licensed. So it's a nice data set to use. This is not important to fine tuning, but this is just making it so that the data sets I got are a mix of code and non-code. So I like to just have it's been found that training large language models on code data just end up doing better on all tasks. So I wanted to make sure that the data set that I'm training on has a mix of 80% non-code to 20% code. And so that's what this flag is allowing me to do. So just a heads up, this data set is like 3.4 million rows. And it's in itself, this has 3 to 2 ratio of code to non-code instructions. It will take a bit of time to download when you're running it, so please be patient. This is just the example formatter. In this case, we're using Alpaca formatting for the instructions. There's a bunch of different instruction formats. Alpaca instruction format is looks something like this. Below is an instruction that describes a task paired with an input for further context, so on and so forth. I actually had already formatted my data set this way, so you can see here that the instruction and the response are already formatted in the appropriate way. So that's all that's happening here. We're just taking a subset of the data. In this case, I think I took 7,500 rows. We don't want to spend all day doing this. And this is just maintaining the mix of data that I wanted. So trying to get like a 70-30 split of non-code to code instructions. So that's all that's happening here. Now we can get back to the QLoRa stuff. So this is QLoRa hyperparameters that we're going to set here. So Sebastian Raska wrote a awesome blog that I highly recommend checking out. And the blog is just LoRa Insights, fine-tuning LLMs with LoRa and QLoRa, insights from 100-something experiments. So this is the blog here. I'll link to it a little bit later. But and so the hyperparameters that we need for LoRa that we discussed are R and alpha, right? So R value is controlling kind of the scope of the reparameterized updates. So it's just the number of parameters that we're going to have, right? Because we have a, N by R and R by N like matrix, right? So R just is essentially dictating how many parameters we're going to be adding to the model. So larger values of R, that's just going to mean more parameters. More parameters are going to enhance the model's capacity to represent more complex kind of patterns. And then alpha here actually is a scaling factor. And this sets the scale of weight updates. So a good value, an optimal value of alpha is going to ensure that the model fine-tunes effectively without overfitting. And it's going to carefully balance new data learning while preserving the existing knowledge. Larger values of alpha will place more emphasis on fine-tuning data. So typically, you want to choose a alpha value that is 2 times the R value. So that's why I chose 16 and 32 here. And I chose relatively small values because remember, the higher the R, the more parameters you're going to choose, fine tune. In this case, setting an R to 16 means that we're going to be adding about 6 million parameters, trainable parameters into the model. And then the LoRa dropout here is just typical dropout rate that you have in neural networks. And so in the paper, they found that setting LoRa to 0.1 for models up to 13 billion parameters is a good choice. And then if your model is larger than 13 billion parameters, you want to use a LoRa of 0.05. So definitely check out that blog by Sebastian Raska. It's a good one. Tons of great experiments and results in here. All right, so now let's talk about the prepare model for K-bit training. So this is essentially a helper function that does a whole bunch of stuff for us. It's going to set the gradient requirements of all the model parameters to false. So it's just going to freeze the model, prevent it from updating. It's going to cast all parameters that are not already in 32-bit floating point format to be in 32-bit floating point format. So if the model is loaded in a lower precision, like 4 or 8-bit, or it's quantized, or if we have gradient checkpointing enabled, this is going to ensure that the inputs to the model will require gradients. So this is done by either enabling an existing function in the model or by registering some forward hooks. It's just then going to check for compatibility with gradient checkpointing. And then if everything's compatible, just enables gradient checkpointing with appropriate arguments to make the training more memory efficient. So just pretty much this function just ensures that the model is ready to be trained under the constraints necessary for QLoRa. Get PEFT model. This just facilitates PEFT by just wrapping a pre-trained model with some specific configuration so that we can have more efficient adaptation to new tasks. So we're going to take an existing configuration from the model using a default if none is set. In this case, we have the LoRa config. We're going to adjust the PEFT configurations, just essentially construct and return a PEFT model that's aligned with the task that we are doing. Here is the training argument. So this is pretty standard, straightforward stuff. Output directory is where we're going to be saving our checkpoints at. Auto find batch size is nice because this means that we're going to automatically discover a batch size that's going to fit our data, which will be useful for preventing out of memory errors. Set this to debug so that we're logging information during training. Optimizer, we're using paged atom 32-bit. So you might need to make a choice between this or paged atom W32-bit. So if your GPU is capable of supporting the quantized optimizer, it's recommended that you use it for training. But if your GPU does not support the optimizer, then best to stick with full precision. So in terms of performance, both options are going to be similar, with 8-bit being a little bit slower. But most optimizations are going to work well with this quantized optimizer. So the difference in training speed should be minimal. Number of steps to save, your checkpoints, how often we want to log, initial learning rate set to be pretty low, just the regularization parameter here to prevent overfitting. Just training for 125 steps, just a small number of steps to, let you go on with your life. And yeah, the rest of it is pretty straightforward stuff. Warm-up steps is just the number of steps to linearly increase the learning rate. Brain float, and pretty much that's it. That's all those parameters that you need to worry about. So then we have the SFT trainer. This is actually what's training the model under the hood. That like once you define everything, you just put everything into the trainer and you let it rip. And that's what's happening here. So we pass in our model, the training arguments, the PEFT configuration, tokenizer, the formatting function that we defined earlier, your training data set, validation data set, sequence length of the model. This is just to map stuff to the data set. Packing equals true means that if we come across a sequence that doesn't fill up our entire sequence length, that will fit like the next example into it. So that's what that means. So that's it. So what is it that we're actually training when we're training here? So remember, when training with QLoRa, the original pre-trained weights of the language model are going to be quantized to 4-bit, and they're kept fixed or frozen during the fine-tuning process. So during the fine-tuning phase, QLoRa is going to train a small number of parameters in the form of low-rank matrices. And then the training process is going to involve updating the weights in a way that the new knowledge from the instruction tuning data set is going to be incorporated into the model without updating the weights of the additional model. So we're actually saving these small adapter weights, right? Because we're adjusting these low rank matrices while keeping the original weights static. So basically the weights in QLoRa is just representing kind of the knowledge the pre-trained model has. And during the fine tuning with QLoRa, a small subset of this knowledge is going to be adjusted to improve or adapt the model's performance on some specific task. And then we just let it train, and there we go. Once we let it train, we save the model so we don't lose it, and then we can we can now merge the model here. So you can just push your adapter weights to the hub, and that's fine. Or you could take your adapter weights and merge it with the model, and put that into the hub. So that's what I did here. I took the original model with our adapter weights and merged them together, and then I pushed it to the hub. And now we can kind of test the model output here. So this is just some helper functions to um, get outputs and format um, our examples. So here, this is the example we're going to run with. Uh, so pretend you're a prolific author, tasked with writing a textbook, so on and so forth. And this is kind of like the ground truth response. And here's kind of what the model predicts to do here. Right here. So it's writing a book about biochemistry, essentially, what it would teach. And so the model, if we were to give this to a base model, it would just kind of do next token prediction and completion. But in this case here, it's actually following the instructions quite nicely. And so that is it. I know I went quick. I'm going to share links to notebooks with you guys. Do not worry. And I'll drop those here for you guys. So I'll stop sharing, hand it back over to Dimitri while I pull up some links for you guys.
Cool. Cool. Thank you for this presentation and sharing the code. So yeah, I hope it was very interesting for all. And we have some questions. Let's look at them and answer. So if you have the question, please also ask them on Slander, and we will start. So first question about in which situation select fine-tuning, full fine-tuning, or pref.
I think you should pretty much always choose PEFT. That's pretty much best practice and standard at this point, because time is money, resources are money. So you want to minimize how much time you spend on GPU and resources as possible. So you should always favor PEFT.
Yes, but if you have the money time, you can fully fine-tune or
Yeah, yeah, yeah. If you got money and time, yeah, and resources.
Resources. Second question about training methodologies. So you describe some good list of methodologies, and what do you think there are some interesting which will be good for the future, which have the potential in the future?
It's a good question. There's one I think it's called is it GPTQ. So that's like post training quantization. I think that's an interesting method. Like, but yeah, of like the methods that we showed for LoRa methods, I haven't played around with all of them yet. I'm hoping that it becomes easy to do so on soon. But for right now, I think going with QLoRa is probably going to be the standard and the best thing to do.
Good. Yeah, more question about papers about you talk about where to find more question. I think the answer is archive, but maybe you have other source.
Which question are we looking at?
Where I can find more good paper about these models
Okay.
to read more. Yeah.
So about the models themselves. DeciLM 6B, we didn't release a technical paper for that yet. We do have a technical blog. So if you type in DeciLM 6B, that should take you to that blog. In terms of finding papers about maybe the methodologies, archive, of course, is going to be the best place to go. Archive, and then also like just reading some of Sebastian Rashka's musings on the topic of LoRa is going to be good for you to kind of understand what's happening a bit better and learn from his experience.
Yeah, so next question about does the model lost quality uh, with double quantization, and for what projects I will be not it will be not a problem.
Not discernible quality, right? Like for the savings you get in time and compute and memory savings, the little drop in accuracy, worth it, worth it. So you should pretty much always use, these kind of parameter efficient methods. It's just worth it.
Yeah. About changing the code, can you please tell how the code need to be changed when we want to do a single node multi GPU distribution training of the same script?
Um, I've never been fortunate enough to work with multi GPUs. I'm GPU poor. I only ever have one GPU to work with, but I'm sure that could. Hugging Face makes everything really easy. Like the abstractions of Hugging Face makes everything really easy. I'm sure it's probably just a single line in the training arguments. But yeah, I'd try googling that, just multi GPU with SFT trainer, and see what comes up.
Yeah. Will you share the code? Yeah,
Yeah,
we will
yeah.
share the code.
Let me drop the link for you in our private chat here, Dimitri. If you take a look there, I'll have the
Yeah,
and then you can share it with the rest of the crew.
yeah, we will share. Thank you. Um, Next question about would you recommend using LLM like DAISY 6B for sequence qualification?
Yeah. Uh,
Sequence qualification.
mhm. Yeah, I mean, you could definitely use a 6 billion parameter model for that, or you could use something smaller, like I think BERT. I think BERT might be better in that case, smaller number of parameters. So for small classification tasks like that, maybe just use a smaller model. This is a good question. So RAG instead of PEFT. So these are kind of two different things, right? Think about what it is that we're doing with. So in general, you fine tune a model to change the behavior of a model, right? That's why we fine tune a model. Retrieval augmented generation is doing just that. It's taking additional uh, content and injecting it into the context window of the model so that it has kind of more up to date kind of knowledge that it can reason over. Um, right. So that's typically what you'd use retrieval for is that purpose. But fine tuning is changing the behavior. Okay, what do I mean by changing behavior? Now let's say that you want your large language model to only ever output stuff. You give your large language model some input text, and you want it to take that input and then output a corresponding JSON, right, with the appropriate keys and values, right? Now, of course, you can do this with few shot examples, right? You can, in context, do few shot examples so the model knows how to go from raw text to JSON, right? But what happens when you do this, right? For one, you're adding additional tokens, and maybe for one call to the model, that's not too bad. Maybe for 10, it's not too bad. But if you got 100, 1,000, 100,000 users, that cost of additional tokens adds up, and you have to pay money for that. Well, in that case, you might want to just fine tune the model so the model now learns how to go from you're updating the weight to the model, changing the behavior of the model so that you don't need to do any in context learning and is able to go from this raw text to this JSON output because that's the behavior you wanted to do. So hopefully that. Let me know if that was clear or not.
Yeah, I think good. So thank you for this presentation from your side, and thank you for all who was with us today. I think if will be some question, we can continue in our Slack channel to speak in, and I will be happy to see you all next week on our next webinars.
Awesome. Yeah. Thanks for coming. Sorry that we took so long to get started, but I appreciate you guys being here.
Yeah, thank you.